We're going to take our universal law of gravitation equation, and we're going to manipulate it to help us solve for the acceleration due to gravity at different points on the Earth's surface, okay, or away from the Earth's surface. On the surface of the Earth, we know that the acceleration due to gravity is 9.8. Good, 9.8 meters per second squared. As you move away from the center of the Earth, what would we expect to happen to the acceleration due to gravity? It would decrease, right? When you get to the moon, we've decreased to a level of 1.7 meters per second squared. So at a distance between those, or a spot between those two things, our acceleration due to gravity should fall somewhere in that range, right? So we're going to take this equation. You do not need to write down all of these equations, okay? The only one that is new that we're going to be focused on is this last one here. But I want to walk you through how we get to the first one to the last one, okay? So we take our gravitational force equation. We're going to manipulate that. We're going to assume that one of the masses is the mass of the Earth, okay? Because we're looking at the acceleration due to gravity from the Earth, but at different locations or different radius from the Earth, different distances from the Earth. Okay, so one of them is the mass of the Earth. So I'm going to substitute M1 for ME. Okay, all I did was put in the mass of the Earth there. Okay, are we good with that so far? Second thing that we're going to do is we're going to substitute M times G for FG. Right? The mass of the object times the acceleration due to gravity is equal to the gravitational force. Yes? Okay, two different ways we can solve for the gravitational force, so we put those two together into one equation. So now we've got the M, which is the mass of the object, here and here. When they're in the numerator on both sides, what can we do algebraically? We can cancel. So if we have M2 on both sides, I'm getting rid of M2, and that leaves me with the acceleration due to gravity is equal to the gravitational constant times the mass of the planet times the radius squared. Right? The acceleration due to gravity. So if we plug in just... hold on, we'll do that in a second here. This is ME for mass of the Earth. Right here. ME for mass of the Earth. Okay, so if I solve this problem with the assumption I'm on Earth's surface, I say G equals big G, 6.67 times 10 to the negative 11th. Oops. Times the mass of the Earth, 5.98 times 10 to the 24th over r squared. So the radius here, if I'm assuming on the Earth's surface, I'm just going to use the radius of the Earth. 6.38 times 10 to the 6th squared. And we're going to see what that comes out to be. Okay, hopefully you know what it's coming out to be, but I want to prove it mathematically. Okay, it should theoretically come out to what we know the acceleration due to gravity is equal to. So solve that in your calculator and see what you get. So what did we get? 9.799, right? 9.8. Okay? Roughly 9.8 meters per second squared, which is what we know what we know the acceleration due to gravity is on the Earth's surface. The thing that we have to think about when we do problems like this specifically is that this value, that radius, has to be from the Earth's center to the distance of our object. So if our object is above the Earth's surface, we have to add that to the radius of the Earth before we put it in and square it. That's where this trick will come. If we're talking about the acceleration due to gravity on a different planet, you'd put that planet's mass in for mass of the Earth. Okay, so you can think of it as mass of the planet, but usually we're talking about Earth. Gravitational constant, or big G, stays the same the whole time. Don't forget to square your radius, because I know you will. Okay? Questions? All right, let's try one. What's the acceleration due to gravity? You have to know, when we ask for acceleration due to gravity, that's little g. Gravitational force is Fg. You have got to know the difference between those two things. Okay, they're very different equations. Fg is gravitational force. So that would be when we're solving for what's the force between two objects or whatever. That's Fg. Okay, so here's my Earth, and here's my, slightly exaggerated mountain. Okay, so the radius I want is the distance from the top of the mountain to the center. Kind of looks like a little clown. Okay, we're looking for this total distance, okay, which means the radius that you plug in is the radius of the Earth, 6.38 times 10 to the 6th, plus that value, 8848, okay? You will recognize in your calculator, when you add those two together, this value is so small in comparison to the radius of the Earth, it won't look any different if you put it back into scientific notation. So I really recommend that you keep that whole number in to square it. Okay, does that kind of make sense? If you plug this in, 6.38 times 10 to the 6th plus 8848, and you put it back into scientific notation, it's still 6.38 times 10 to the 6th. Okay, so keep the whole number. Don't put it back in scientific notation before you square it. Okay. We're solving for acceleration due to gravity, which means little g, mass of the Earth, over r squared. If the gravity on a hypothetical planet is 3.21 meters per second squared and the mass of the planet is as follows, what's the radius of the planet? So we're not talking about Earth. You're not dealing with any of the Earth constants. You're doing this one of a separate planet, right? But the gravitational constant stays the same, so big G still works. Alright, so we know little g is equal to 3.21. Mass is equal to 4.12 times 10 to the 21st. And we're solving for radius. So algebraically, the first thing I usually do would be to move g over, divide g, go to the other side. There's lots of different ways you can do the algebra. I do that first. I know it's probably not the most efficient, but whatever, that's what I do. Okay, so when I divide that over, I get 4.81 times 10 to the 10th equals 4.12 times 10 to the 21st over r squared. When my variable's on the bottom, I can switch these two places. Okay, which means I'm going to take 4.12 times 10 to the 21st divided by my answer. And that gives me r squared. And then I square root both sides. These equations are specific for satellites, so you want to put that on your equation sheet as satellite equations. These are specific for things in orbit outside of the Earth. Okay? So satellites that move around the Earth are in uniform circular motion, so they kind of are a combination of these two equations. You are welcome to follow the derivation of the equations in your textbook, but I don't walk you through all of that. Something that you should know about satellite orbits is that they stay in the same their orbit itself means that they are a certain distance from the Earth throughout their whole travel, right?
That is pi. Is that pi?
That is pi, yes. It has to do with that circumference, equation. Wow,
Yeah.
I'm having trouble. Okay, 2 pi. So the first of which tells us the velocity of a satellite in a circular orbit. Again, this is derived from a combination of the circular motion velocity equation as well as your acceleration to gravity equation. And then the second one tells us, what does t tell us?
Period.
The period, which is the time required to make one trip around the Earth. Okay, it's important to see this is r cubed. R cubed right here. Your book gives a much more intense calculation here. The equation is like much bigger, and this one's better. It's different than your book. Okay, so we have 2 equations that are specific for satellites only, things that are orbiting around the Earth. How far away it is from the Earth's surface. So we're going to solve for r first, and then we can subtract out the radius of the Earth, right? And that would give us the distance from the Earth's surface. So look at these 2 equations. The first thing we need to do is that if it's going to rotate, if it's going to have the same period as the Earth, what's the period of the Earth? How long does it take the Earth to spin one time?
1 year, 365 days.
Not around the sun.
Oh, 24 hours.
24 hours, right? So if we have this Earth spinning, and the orbit of the satellite is the same rate as the Earth, okay, not really the same rate, I'm saying it wrong. It has the same period as the Earth. That period has to be 24 hours. But we can't put period into our equation in hours. So the first thing you do is convert that to seconds. Put that 24-hour period into seconds. I think I'm going to work here. All right, here we go. Can everyone envision what this satellite's doing? Right? If there was a satellite that was in our sky right here, that means it would be in our sky the whole time, right? When the Earth rotates, it rotates, and we can see it the whole time. Right? We don't have anything in our satellite right now or in our view that looks like that right now. Okay, so t equals 24 hours because it takes that long for it to spin one time. In seconds, that's what? 86,400 seconds. That's t. Okay? Our goal is to find radius. So let's look at our equation to help us solve for radius. Of a satellite, it's t equals 2 pi square root sorry, I can't find it on my sheet. R cubed over GME. So we have everything else we need in the form of constants, right? The only information that we needed here was to figure out how long does it take to make one path, and that tells us how far away from the Earth it is. Okay? So let's solve for it. This value right here just came from me multiplying g times mass of the Earth. That's what that equals, 3.98 times 10 to the 14th. Okay, so I just combined one step right there. Okay, so algebraically you need to move 2 pi over first. In your calculator, I'm telling you right now, you have got to be either putting parentheses around 2 pi or divide by 2, divide by pi. Okay, because if you go 86,400 divided by 2 pi, it divides it by 2, then it multiplies it by pi. So you have to do parentheses around that 2 pi, or you do divide by 2, divide by pi.
So like parentheses around 2 and top?
So I'd go 86,400 divide by parentheses 2 pi, close parentheses.
Okay.
And I got 13,751 equals square root of r cubed over 3.98 times 10 to the 24th. So what do I need to do next? What's my next step? Yeah, I have to square both sides to get rid of the square root. So I square this side, and I square this side. Okay, if you haven't noticed, this chapter's a lot of algebra. Times 10 to the 8th equals r cubed over 3.98 times 10 to the 14th. Now if I have my r cubed here, I need to multiply those two together. And that gives me 7.52 times 10 to the 22nd. Okay, I'm writing these numbers out here, but I'm not taking them out of my calculator, so just FYI. Okay, and that equals r cubed. Does everyone know where the cubed root is on their calculator?
Yeah.
It's in the math function, so this math button right here. Do you have a math button? No. Okay, this distance is from the center of the Earth to the satellite. Okay, so here's my satellite. This is the radius that I just solved for. I only want that distance. So now I take this number, 422, blah, 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 and I subtract out the radius of the Earth. So minus 6.38 times 10 to the 6th, and I get a value of, perfect, times 10 to the 7th. 1, 2, 3, 4, 5, 6, 7. Yeah, 0.38.
Wait, when did you get that?
So we took this 422 number. That's the total distance here to here. And I only want this little x. So I subtracted out the radius of the Earth. So I take this number minus 6.38 times 10 to the 6th. And that gives me this value. Okay? So that's many meters above the Earth's surface. So the things in this chapter that you need to be aware of is that you'll see things that say above the Earth's surface or from the Earth's surface or 2 radii from the whatever. Okay, so you have to read and decipher those context clues to determine your radius. That's something that will trip you up. Squaring your radius. You'll forget to do it, even though I've reminded you 5 times. And converting your period into seconds always. Okay, those are things that you need to be looking out for. At what speed is that satellite orbiting? So we want to find the velocity. That's right. That's right. So Jack asked a good question. He said, for the radius, does it mean the final answer that we just had? And that's no, because that's from the surface of the Earth. We need that whole 422 blah, 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 blah number to use as our radius to find the velocity. The final answer of our previous problem was from the surface of the Earth, but we always need the radius from the center of the Earth out. Okay? So the equation for velocity is not 2 pi, just square root of g me over r, right? Okay, so this radius has to be that 4.22 times 10 to the 7th. I wrote it out all the way on the previous problem, so you can write it out all the way if you want to. That's fine.